Hello, I'm Ron Bilyeu. I'd like to welcome you to our training program, Current Ramping. Before we get started, I want to talk about when would you make a choice and when is a good choice that you would use your lab scope and a current probe to do some dynamic testing. Well, let's look at an engine management system. An engine management system has the computer and inputs and outputs. Basically, the inputs, the computer is looking at voltages. Lucky for us, those voltages are usually 0 to 1, 0 to 5, or 0 to 12. They may be analog, they may be digital signals. Now these numbers, 0 to 1, 0 to 5, 0 to 12, may indicate mechanical movement like a throttle position sensor, pressure like a manifold absolute pressure sensor, airflow like a mass airflow sensor, oxygen content that would infer air-fuel ratio or whether we are richer or leaner than the stoichiometric air-fuel ratio. But basically the inputs, the computer is looking at numbers. It's a really good fancy calculator and timer. Now as it looks at these numbers and looks at its programming and lookup tables, it's going to make a decision to control outputs. Now in the outputs, we're looking at controlling relays. For example, when you turn the key on, the computer may ground a fuel pump relay for 1 to 2 seconds, which allows power to the fuel pump. If the computer sees an RPM signal, then it may allow the fuel pump to continue to run, but it'll initially turn it on for 1 to 2 seconds. The computer may control outputs such as ignition coils, fuel injectors, solenoids. All of these things, if you think about the relays, solenoids, injectors, pump motors, blower motors, cooling fan motors, there's something common to all of these outputs. What is common is they all have a coil of wire, and they're basically classified as an inductor. If you think about it, let's look at from the rear bumper to the front bumper of any late model vehicle, how many components, think about all the motors, the solenoids, the relays, ignition coils, injectors, how many items from the rear bumper to the front bumper have a coil of wire? Any of these items, the best way to dynamically check these items with your lab scope would be current ramping. So the question comes, does the component you would like to dynamically test with your lab scope, does it have a coil of wire? An electric fuel pump has a coil of wire. Ignition coils have a coil of wire. Solenoids, whether it's a turbo boost solenoid, a torque converter clutch solenoid, a 1, 2, 2, 3, 3, 4 shift solenoid in a transmission. Injectors have coil of wire. Even relays have a coil of wire. That's when you would make the decision on using your current probe to current ramp or to dynamically see current flow over time. Remember that your scope from left to right is time and bottom to up is going to be amperage. Your current probe is going to take this amperage and convert it into a signal that we can see on the lab scope. Now, to make it easy to get into these different circuits, and as you can see here, I have a power distribution box with several fuses. I can use a fuse buddy that will allow the circuit to still be protected with the fuse and also allow me to attach my current probe, giving me access in series to that circuit so that I can current ramp that circuit. So anything that is on that circuit, for example, if this circuit was the power supply to all of the ignition coils, I would make one connection and I would be able to see every single time that the coil fired, I would be able to see the current ramping or the current waveform. If I was attaching to an output fuse that was for injectors or a bank of injectors, when I went to that power distribution box, the source with the fuse buddy, remove the injector fuse, go into that circuit, I'm going to see every time that injector fires, I'm going to get a dynamic waveform pattern of that injector. The first component we're going to go over testing is the in-tank fuel pump. Accessing the in-tank fuel pump current waveform, I prefer to be on the power side, the high side of the circuit. Obviously, we can access that circuit by utilizing the fuse buddy, wherever the fuel pump fuse is. We may also access it as the power comes off the fuel pump relay. In the case of Fords, a lot of times I will find the inertia switch, which is typically in line with the fuel pump, and it may be easily accessible in the trunk area or in the kick panel, the driver or passenger kick panel, where I can access that and quickly get my current probe around the power feed. One of the first things we want to look at is what I call fuel pump rush-in current. This is the initial hit of current flow that's going to energize the field and get the armature turning and also the liquid fuel. You really want to see a vertical line straight up like a rocket taking off. If you measure this, you may see that your rush-in current exceeds the protection of the circuit. The fuel pump may be on a 10 amp circuit, but the rush-in current might be 15 amps, which should get you thinking about, well, how's the fuse going to stand up to a 15 amp draw when it's only a 10 amp fuse? The time is probably less than 1/10 of a millisecond. That's 1/10 of a thousandth of a second. There's not enough time to open up the fuse protection. We want to see a vertical line. We don't want the lazy movement as the pump first goes into motion. So I like to see, maybe I might use the scan tool to energize the pump or have an assistant turn the key while I am focused on the lab scope with my current probe attached so that I can see that vertical line shoot up and I can look at my rush-in current. After I've looked at my rush-in current, I'm going to look at stabilized current. Now, as you can see, the pattern observation of the fuel pump is we're seeing the rotational motion of the armature and the brush contact on the fuel pump armature. You can see here that we're measuring, we're not really exactly holding right there at 5 amps. We're kind of dancing above and below 5 amps, which gives us an average of around 5 amps. After that rush-in current, the current flow is going to drop down and it's going to stabilize. This stabilized current, the amperage draw, is a specification you should be able to find. It is published in a lot of places in your information systems. Really, the amount of amperage draw typically falls into an area of 4 to 8 amps. But there will be published specifications on the fuel pump on the particular year, make, and model that you're working on. So, your first two things are to check rush-in current and stabilized current. The next test of dynamically testing your fuel pump is to identify the fuel pump speed. Not all, but the majority of fuel pumps have an 8-segment armature. Once you count 8 segments, what you have really counted is one rotation of the fuel pump. In my mind, I always remember a simple formula. The simple formula is any shaft, crankshaft, fuel pump armature, any shaft that is rotating, one rotation in 10 milliseconds is at 6,000 RPM. And I can deviate from that. If 10 milliseconds is 6,000 RPM, what would half that be? Well, that's a lot quicker, so you would double the RPM. Or you could do the math. The math is 60,000 divided by the time in milliseconds, and your lab scope will provide you that time as you count the segments in the armature to get the millisecond time. 60,000 divided by the time in milliseconds will provide you with the RPM. Because, as it says, it takes 10 milliseconds to make one rotation at 6,000 RPM. There's not really any published specifications on what particular fuel pumps and what RPM they will operate at. So it would not be a bad idea if you started to take some notes as you are current ramping various vehicles. It's probably a good idea after replacement of a brand new pump to go in there and look at what a brand new pump looks like as far as rush-in current, stabilized current, and RPM. If you're not sure that the pump you're working with is an 8-segment armature, where you're trying to figure out what is one rotation, study very closely the pattern observation, the humps. You know, it kind of resembles McDonald's golden arches. Look for a uniform so many counts over where the shape of the armature, the kind of M shape, is repeating itself. There's a possibility maybe you have a 6-segment or a higher than 8-segment pump, but the majority of them seem to fall into the 8-segment. You're trying to figure out, once that repeats, that it is where one rotation is. Here you can see we have a Walbro 255-liter pump found on a lot of forced induction Ford products, and we know that it's an 8-segment pump, so the one rotation there, you can see the time if we look at it. A nice feature of the picoscope is not only that we can see the time at 8.729 milliseconds, but in the bottom right-hand corner of our slide, it's already figured out the pulse per second at 114.6 and did the math for us. So this Walbro 255-liter pump is at 6,873 RPM. The last test that we want to do, first was rush-in current, stabilized current, fuel pump speed, is pattern observation. Because you are dynamically looking at the armature rotating, you can see if there's movement in the armature. You can see if there's poor brush contact. If you start to see every other hump is looking a little different or something in uniform, as you can see in this pattern observation, we're somewhere around 7 amps stabilized current, but you can definitely see the up and down movement in the pattern observation is that we have some play in our armature and we have some poor brush contact. When you are providing information to your customer, you basically provide 3 pieces of information to them regarding the testing that you have done. One is the component that you have tested is okay. 2 is service is required, it's defective, it's bad, it needs to be replaced to put the vehicle back into service. 3rd would fall into this area, needs attention. And let me reiterate this. This is not a substitute to traditional fuel pressure and volume testing. This is one step ahead, as I call it, dynamic fuel pump testing. But it's not going to substitute your traditional static running pressure tests, volume tests. This is above and beyond this. This is dynamic, advanced fuel pump testing. So this would classify this vehicle with this play in the armature and also some brush contact issues would fall into the classification of needs attention. Of course, you know what the customer is going to ask you after that. Well, what's going to happen if it moves from needs attention to service required? You're going to be in what we call tennis shoe mode. You're going to be walking. More than likely, you have taken the time to do dynamic testing and you have found a component that needs attention. Many customers will elect to repair that at this time, which is making your shop more profitable and you're keeping that customer from having a failure on the road. So in summary of dynamic current ramping fuel pump testing, we look at rush-in current, stabilized current, and you should be able to find a specification for that. We want to figure the fuel pump speed and also pattern observation. Do we have bushing wear, bearing wear in the pump? Is the armature moving up and down? How is our brush contact? Now, you start to build your own notes about fuel pump speed and current flow. Let me just give you a scenario here. Let's say we're looking at a pump in which the current flow is within spec, but the speed is really high, like maybe 8,500 RPM. This may sound crazy, but maybe the current flow is normal, but the speed is high because the vehicle is out of fuel. There's a lot of information in this dynamic testing of the fuel pump. Now, I have one more diagnostic tip that I want to share with you regarding fuel pump testing. When you are doing pattern observation or trying to figure fuel pump speed because you're closely looking at the shape of the different contact points between the armature and the brush, I want you to utilize a feature in your lab scope. What you want to do, now you can leave it in a DC coupling when you are looking at rush-in current and when you are looking at stabilized current flow, but when you look at trying to figure out the speed of the pump, and really when you're trying to look at pattern observation for problems, you want to use the AC coupling on your lab scope. Basically, by putting it into AC coupling, you are telling the scope to show you change, show you differential. It is going to enhance your pattern observation, and it will allow you to see problems in the fuel pump a lot quicker. The next component that we're going to look at to current ramp are ignition coils. Just about every manufacturer today has went to an individual coil per cylinder known as coil on plug or coil near plug. Now, we can kind of divide those into two areas. For a lack of better terminology, a lot of technicians have adopted the traditional two-wire coil as fallen into a category of a dumb coil. Because realistically, all it is a primary windings, secondary windings, and a lot of epoxy. So what I have up here on the slide would be considered a two-wire dumb coil, and we will talk about some of the testing we can do with that in reference to current ramping. You can see we have a red wire and a green wire, so I would really have a choice. If I was wanting to look, and it is available to me, to look at the primary voltage waveform, I would make a conductive connection to the green wire, the primary circuit. If I want to current ramp this coil, I'm going to get my current probe around the power feed to that coil and look at current ramping. Or if I have a multi-channel scope, as you see here, I have the ability to look at both. So the red trace line is my current ramping pattern, and the blue trace line is my primary voltage pattern. If you follow the blue line across from left to right, there's a downward turn where the transistor turns on. It's at that point that we start to flow current through the primary side of the ignition coil. Hence the name current ramping. As we're passing current through this coil, we'll see it ramp up. Now we follow the red line coming up at about a 45-degree angle, and then all of a sudden it makes a downward abrupt turn. And if we look at the blue pattern, this is where the spark plug is fired. Because the switching transistor at that point, it was turned on, then it was turned off at the point of firing. So, from the blue line slight turn down, where we start our ramp up on the coil, to where we fire would be known as the coil saturation or the coil dwell time. Most late model vehicles, this dwell time or this coil saturation is controlled in the computer. The computer decides not only when we fire in relationship to where the piston is, but it controls how long the primary section of the coil is energized, known as coil saturation or dwell time. Now, the very top of our amp probe comes to a point which tells me that before we completely saturated or passed current all the way through all of the primary windings, the computer decided to turn off the transistor and we fired, as noted by the firing line on the blue primary voltage. Then we're going to have our spark duration as we're basically dropping over the spark plug gap, and then we have our leftover reserve energy that we can see in the primary pattern. Yes, we are seeing some secondary components, the pattern observation of the firing line, the spark duration, or sometimes referred to as the burn time, which is affected by the secondary, but through mutual induction, we can kind of see what's going on in the secondary by looking at the primary voltage waveform. We are able to do this because we have access to the primary side of the coil. We only have this access on a two-wire coil, as we said earlier, sometimes referred to as a dumb coil. So, we have to have in any system, whether or not it's a two-wire coil, three-wire, or four-wire coil on plug or coil near plug, we have to have some sort of current limiting. Current limiting because the computer decides to control the time that we pass current through the primary, or in some current ramping ignition waveforms, it'll look like someone took a straight edge and just cut the top of the point off of the current ramping. That means either if we have an external ignition module or the PCM is the ICM, meaning the computer is the ignition control module, it will have the current limiting function in it. Or in some cases, the current limiting function may be part of the ignition coil. Obviously, it would not be a dumb coil. It would be a 3 or a 4-wire smart coil. So, if we're dealing with a 3-wire or 4-wire smart coil, first let's look at the 3-wire. We're looking at a power feed, we're looking at a ground, and we're looking at the IC signal, the signal from the computer telling the internal switching transistor when to fire. Inside the smart coil is an NPN transistor, negative, positive, negative. So when the computer supplies positive voltage, the N, negative to negative, is joined. If you want to compare that to old days, that's when the points are closed. Once the computer removes positive P, the negative to negative is opened and the coil fires. So we can look at the P, which keeps the negative to negative closed during coil saturation time. We can look at the power feed to the coil. We can look at the IC signal to the coil, and we can verify that we have a good ground. If we take our current probe and go around the power feed, we can current ramp the smart coil. So here we're looking at a 3-wire. I know there's 4 channels, but we're on different channel. We're looking at 1 ground, 2 IC signals, and current ramping of 3 different coils here. So as you can see, the red and the green are IC signals telling the coil when to turn on and when to turn off. The bottom is the ramp that you see coming up and then firing, so that is our current ramp on the bottom. The top blue line is the ground circuit where you can see a slight deflection in the ground when the ignition system fires. Some systems will monitor the ground to determine the voltage drop on the ground side when the system fires so that we can provide primary ignition fault codes. Some systems monitor the amperage draw to the coils. If the coil did fire, the primary was saturated, the coil did turn on when the computer told it to, Then we'll have a certain amount of amperage draw, and the computer will look at the amperage draw to verify that there is good integrity in the primary circuit. Some systems, this voltage drop will go to another module that may send a digital signal to the computer verifying that the primary did in fact fire. Toyota, Lexus, Scion likes to use an ignition fault circuit. Hyundai, Kia uses an ignition misfire module. There's a lot of variations in our manufacturers, but the root of the information is either looking at voltage drop on the power circuit, voltage drop on the ground circuit, or current flow to identify that we did have good integrity of the primary control from the computer and that the ignition coil did fire. So here is a LS1 coil near plug. Coil near plug, we will have about a 6 to 8 inch secondary ignition coil wire going down to the spark plug. But it has 4 wires. It's going to have a power supply. It's going to have the IC signal when the computer turns on and turns off the NPN transistor in the coil. We're going to have a ground, and then we have a dedicated feedback circuit on that 4th wire. If you connect your scope conductively to the feedback wire, amazingly enough, it looks like you're current ramping that wire, but you're not. You've just made a physical connection to it, which tells us that it's basically looking at the voltage drop when the coil fires to infer good integrity. So the 4th wire in the GM LS series is basically a diagnostic wire. This is a good-looking coil ramp of an LS1 4-wire coil. And the information that's provided there is that we do not have a shorted coil. I can see the transistor turn on and turn off. I could measure that, which would provide to me the dwell or the coil saturation time. I can look at the amperage draw, and because in any engine, 4, 6, 8 cylinder, I'm always going to have other coils that I can compare to. I want to show you what bad looks like. And in this case, we're current ramping an ignition coil that has a short. What we do not want to see is any type of a vertical line, or it may look like a big beer belly coming out. That's a shorted inductor. In this case, it would be a shorted ignition coil. This coil is definitely showing that it is defective. We want to see a nice ramp as we're moving current flow through the primary side of the coil. Here's definitely straight up vertical, dead giveaway. We have a shorted coil. We have no ramp. This coil is definitely defective. I want to talk a little bit about what's going on in our industry regarding coil on plug testing. So the vehicle comes into your shop, customer complains of a misfire, flashing check engine light, you retrieve trouble codes. We'll just say you pulled a code P0304, misfire on number 4 cylinder. You suspect through program response and your past history of working on this particular year, make, and model that you have a defective coil. So you remove the coil on number 4 and move it to another cylinder, and the misfire moves. You have correctly diagnosed that you have a defective ignition coil. When you replace that coil, however, I recommend that you still do some testing. What if the coil is the effect and is not the cause? For example, what if the IC control in the computer was stuck on too long? If the current flow through the coil is controlled based upon the coil saturation time that is programmed into the computer and it stays on too long, the current flow will exceed and you could have an open circuit in the primary winding causing the coil to go bad. Now, You replace the coil, the engine fires up, it runs, pat yourself on the back, you just fixed the vehicle. But what if a day or two later the customer comes back with those famous words that we all love? It's doing the same thing. Immediately you might think, wow, I got a defective coil from the parts house. Or was it that no coil will live because you have a problem in the computer? You've already charged your customer for diagnostic time. You diagnosed it as a defective coil. You've charged the customer and the labor to replace the coil. Now you get to go back to the customer, which has already paid you their hard-earned money, and you get to ask for an additional money to buy a computer and probably to have that computer reflashed, reprogrammed. That will not be an easy sell. Let's test, don't guess. Yes, you confirmed that the coil is defective. Make sure you're replacing the cause, not the effect. I have a unique ignition system that I'd like to share with you. On many Fords that even go back to the distributed ignition system, EDIS, and a lot of coil-on plug systems, you may run into this. I'm first going to show you, and what I have on the slide is a secondary waveform of an individual cylinder. As you can see, the spark plug fired 3 times. At idle and low load events, Ford will use multi-strike capability. This helps to clean up emissions at idle and part throttle, and it really helps with overall engine idle stability. Makes the engine run smoother. Now this is a secondary to try to give you an idea of what's going on as far as the spark plugs firing 3 times in one compression cycle. This is the secondary. Now let's take a look at the primary current ramping. If we look at the first firing event, it looks like a typical current ramping good pattern. We can see where the transistor turns on. If we measured the bottom of the triangular shape, we would get the coil saturation or dwell time. We have no vertical line, no big beer belly sticking out. We don't have a shorted coil. We can measure the overall amperage draw to the ignition coil. But it's the second and third that a technician may think, from learning current ramping, remember I told you I don't want to see a vertical line, but in the second and third strike, we have a vertical line. This is an exception to the rule. This is normal. We do not have a shorted coil. When we are observing the pattern to look for the vertical line or a big beer belly on that current ramp, we want to look at the first firing event. The second and third firing events happen so fast and the current passes through so fast that we will have the vertical line, which is normal in this Ford multi-strike current ramping. All of our ignition systems will have some form of current limiting, either a current limiting resistor or the time of coil saturation limits the current. It's easy. Just think about the math. If I have 13.5 volts going to the primary side of the coil, and if we kept the math simple and said, well, the primary winding resistance is 1 ohm. If we plug in Ohm's law, that ignition system should draw 13.5 amps of current flow. I've never seen an ignition system draw 13.5. I think the highest I have ever seen was some wasted spark GM systems, Magnavox systems that drew 9 amps. So there has to be some sort of current limiting feature built in. And the reality of it is, it's not uncommon to see a primary resistance number of 0.5 ohm. Well, what would it be if we plugged in Ohm's law at 0.5 ohm and 13.5 amps? You're looking, or 13.5 volts, you're looking at 27 amps. There's no way the primary windings in the coil could survive this. So whenever the current limiting section fails, we're going to have a failed coil. Again, make sure that when we replace the coil, we're replacing the cause and not just the effect of some other problem. The next area we're going to move into is current ramping of solenoids and injectors. There can be some big advantages to this. I'd like to give you an example. Let's say we have a front-wheel drive automatic transmission vehicle that is setting a 2-3 shift solenoid trouble code. Now, to get to the shift solenoid pack, the transmission cover has to be removed. It's a front-wheel drive vehicle, and this is going to require 6 hours labor. However, if I can get to the power feed wire to the solenoid pack in the transmission and get my current probe around that power feed wire to the solenoid pack, at that point in time, I could take my scan tool and energize the 1, 2, 2, 3, 3, 4. I can energize the shift solenoids. I can energize the torque converter clutch solenoid. And I can look at my current ramping waveform pattern and identify if there's any problems in that waveform. For example, this is an injector, but it could be a solenoid. They're all basically spring-loaded passages that are opened with electrical current flow. So what do we know about this? Well, it could be an injector or a solenoid. If we look as the solenoid or injector is energized, the current starts to flow, then we have this bump here, and then we continue on. I don't have any measurements here, so I can't tell you the duration of the time of the solenoid or the injector. I can't tell you the amount of current flow, but I could measure and provide that information. But right now I'm just focused on what do I know about this injector, or if it happened to be a current ramping waveform of a solenoid, I know that it opened. That little bump about halfway up the current ramp is a dead giveaway that the solenoid opened. In the early style injectors, when they had a pintle, they called this the pintle opening. Inside the programming of the computer, if this was an injector, this is known as injector offset. At a particular voltage, through the design of the injector by the manufacturer, they will know, and it is programmed into the computer, at what point in time will the injector open up at this particular voltage supply. The computer has to know this to control fuel delivery in the engine management system. So the answer to the question, what do we know about this injector? It did open. We know that for a fact. Or in the case of it being the 2-3 shift solenoid and a hard to get solenoid pack in the transmission, we know that it did open. We can also measure injector duration, as you see here. We can measure from the time the current flows to the current stops, and we can see that we have 2.53 milliseconds. We can also measure that this injector had a current draw of 0.8 or 800 milliamps or 0.8 amps. We can measure the current flow of the injector. We also have the ability to compare injectors on the vehicle for pattern observation. Again, just like the ignition coils, we do not want to see a short or a vertical line or a big giant beer belly. We want to see a defined opening. We want to make sure that the injector current flow matches the other injectors on the vehicle and is in spec for that particular injector. We basically have two different types of injectors in our business. We have low impedance and high impedance in the gasoline injection arena. So this would be a saturated injector that normally has a resistance value of 12 to 16 ohms, figuring a nominal voltage of 13 volts. We should see somewhere between 3/4 and 1 amp draw on that, but they should all have the same amount of current flow and especially the same injector offset. That is, we're going to measure the opening time of the offset. The other type of injector is known as a high impedance or a peak hold injector. In this case, we'll have a certain amount of current flow to get the injector open, and then we will sustain a lower current flow to maintain the injector opening. These are injectors that will have a resistance value of approximately 1 to 4 ohms. They usually draw somewhere close to 3 or 4 amps, and they hold around 1 amp. As you can see here, we have a peak opening current flow of around 3 amps and a hold of just a little over 1.2 amps. The next slide that we have here comes with the question, what's wrong with this solenoid? It doesn't take very long to look. It could be a fuel injector, it could be a solenoid. It didn't open. I have no defined opening point. So even though I may have current flow through the solenoid or the injector, I did not have mechanical movement. I didn't actually have a disc or a pintle, a valve that opened internally in the solenoid or the injector. Therefore, whatever this is supposed to do, flow transmission fluid through the valve body, flow fuel out the fuel injector, it's not going to get the job done. This is definitely a problem, and it's well defined that we did not have a defined opening point. Here's a good solenoid with a defined opening point. Keep in mind how many components on the vehicle is going to utilize some sort of a solenoid, fuel injectors. It's very valuable. Some of them may be hard to get to, but again, finding the circuit in the power distribution box, using a fuse buddy, getting your current probe in that circuit, commanding the device to open or close with a bidirectional test of the scan tool, or turning on the device and watching to see if we have a defined opening, that it is drawing the correct current, or that it is open for the specified amount of time that we would expect. I have a case study that I'd like to share with you that came to my shop. It was a Ford Lightning, which is a 5.4 liter supercharged Ford Lightning pickup, 187,000 miles, and he had the injectors cleaned a couple times, and it seemed to improve the vehicle's drivability, but never really felt like it did when it was new. He was the original owner of the vehicle. He finally decided if cleaning the injectors helped a little bit, then new injectors should really get it back to the level of power and performance and drivability when it was new. So he elected, and this was done by another shop, to have the injectors replaced totally. So after the injectors were replaced, he then started to have more problems than he had before. He had a check engine light setting a PO 171 and 174, which means that the computer is seeing an abundance of oxygen in both banks, which could be attributed to a lean condition, causing fuel trims to migrate probably over 10% in different load cells, which sets those codes, PO 171 and 74 for bank 1 and bank 2. It's running poorly, worse than it ever has. It's down on power, and if he forces it to try to get it to make power, he's really concerned because he's starting to hear audible spark knock, which is really dangerous for a forced induction vehicle. The vehicle was presented to us. We run various checks and diagnostic, and we come to the point that the injectors are not working properly. Like many shops across the country, I do not own an injector flow bench, but I have a company that I utilize, and I decided to send the injectors out to be tested. Well, this particular Lightning pickup, as you can see, there's the 5.4 engine. There's me removing the injector. You can see in the performance world, those are known as the 42 pound an hour flow injectors, or the mean greenies. We sent those new injectors out and had them flow tested. The results that came back said that the injectors were flowing like 30-pounders. That's huge. If this engine from Ford required a 42-pound-hour injector, and that's rated at 43.5 psi, and they're only flowing like 30, we are successful in our diagnostic, and we've got to find out why these new injectors are not what they're supposed to be. So when we got the injectors back, we started doing some bench testing, checking the injectors by utilizing dynamic testing, which is current ramping of the injectors. So we can see what the current flow is and the opening time. We already know that they only flow like a 30-pound-an-hour injector, not a 42-pound. And that's enough information to say, hey, we've got to get, these injectors that were purchased were obviously a problem. Now, the shop that I sent them to told me that they noticed that they've seen a rash of this problem, that the market is full of manufacturers that are trying to copy quality injectors. So this is kind of what we would call a knockoff of a quality Bosch 42-pound injector. So what we'd like to do here with you is review and go over those bench tests that we did, which also will enlighten you and your testing capabilities of current ramping. Let's get set up on the bench. Okay, we're going to do some current ramping bench test here. I have my injector tester, which will provide a consistent injector on time and power to the injectors and pulse them in a preset stage. So the first injector that I'm going to test is the Bosch injector. So we're going to plug into the Bosch injector and connect our current ramp probe. Now we're going to energize the injector, and I've captured this information. So let's take a look at the Bosch injector. The first thing I want to measure is the injector offset, which is the amount of time at a voltage level that it took for the injector to come open. And as I measure it here, you can see that the injector offset at this voltage level provided by the injector tester box was 957 microseconds. The injector, the Bosch injector, was 837.5 milliamps draw with an injector offset, as we see here, of 956.7 microseconds. I'm going to leave the measurement cursors up for the Bosch injector, and I'm going to move to the knockoff injector. Going to remove the quality Bosch injector and plug in the problem injector. We've got that set. The injector tester box is at the same pulse time, and we're going to pulse that injector and freeze it. You can already see that we have a wide variation of the injector offset. I'm going to readjust my cursors for the knockoff injector to get its injector offset. And it has an offset of 833 microseconds, nowhere close to what the Bosch injector. And the injector's current flow, 978.3 milliamps. So we have a variation in injector flow that was done on a flow bench, that the knockoff Bosch injector flows like a 30-pounder. It also has the wrong injector offset, which is programmed into the computer the time that the injector, it takes for it to open at different voltage levels. And the overall current flow is nowhere near the original equipment quality style Bosch injector. I want you to be aware of There's more and more of these in our industry. So make sure that you're looking for, when you're replacing an injector, that you are getting the same OE quality, or you're going to run into problems like my customer did. He had slight problems, but the problems got worse when we put an injector that only flows 30 pounds, the injector offset is off, the amount of current flow that the injector draws off, it's never going to work. We have to replace it with a quality set of Bosch injectors. As you can see on the left-hand side is the knockoff Bosch injector. You can definitely tell that that injector is drawing more current. The red dotted line going across the top is the total current draw. Remember that the injectors were pulsed at the same voltage and the same time. So these changes are all based upon the internal dynamics and the engineering build of the injector. You can also see that the injector offset at this particular voltage, what time did it take for the injector to come open, is huge. 833 microseconds versus 910. This is going to cause lots of problems in the computer trying to control this injector because of the opening offset time, the amperage draw against the computer drivers, and the fact that the injectors flow only 30 pounds an hour versus 42 pounds an hour. In summary of our current ramping class, I'm sure you can see the major benefits of utilizing current ramping. We took a look at ramping the fuel pumps, injectors, solenoids, ignition coils. Remember, how many items have a coil between the rear bumper and the front bumper? If you want to dynamic test those inductors, you want to utilize current ramping. I'm Ron Bilyeu, and I'd like to thank you for watching this program and look forward to other events. Thank you. Please feel free to contact AVI for additional information.